Good morning, everybody, and I thank the organizers for the invitation and for organizing this in the UK meeting. And what I'll do in the next 15 minutes is to give you an introduction to genomics and the genetic testing techniques that one uses in genomics, largely about the two major approaches which I'll talk about, and give you a flair for what next generation sequencing has to offer. But from the look of the audience, it tells me that most of you already know most of the content, but for those of you who are still new, please bear with me. Okay, some mandatory declarations that we work with a number of companies for transfer technologies and for funding our research. So I come from the Institute of Genomics and Integrative Biology, which is in Delhi. That's the building. If you're ever in Delhi, please do stop by. We'd be happy to host you. We had Professor Devendra Kumar 2 weeks ago there for the physician workshops. Largely my lab works on two major areas. One is on genetics and developmental biology, which is something of fundamental interest to me. But for this audience, more interest would be the functional genomics aspect, where you look at personalized and precision medicine in humans. How do you implement it in a developing country like India, and how do you create rare disease models that can be used in precision medicine. But let me quickly go over the textbook definitions of it. Many of my colleagues get confused between genetics and genomics. Please remember, genomics is a subset of genetics. Genetics is the primary discipline that looks at the study of specific individuals and their role in inheritance. And the genomics is a subset that looks at the entire genetic makeup and its interaction with the environment, including the lifestyle disorders. So both of these subjects are very much intertwined among each other. I don't need to introduce largely the key ingredient that we're going to talk about is the human DNA, which is present in almost all the cells that we have. And classically, historically, what has happened is one could read this DNA using a very famous technique developed by Frederick Sanger in UK, for which he also got a Nobel Prize, which is popularly called the Sanger sequencing methodology, by chain termination. Okay? So what will happen here is you take small fragments of DNA, put them into vectors, and be able to read out these vectors using a methodology, and be able to generate chromatograms and be able to find out what is the DNA sequence. This was the state of the art for the practically the late 70s to the early 2000s. Okay? This led to the first reference human genome being put together by this technique, but largely there are two approaches one could take. One was either you could sequence, if you consider the human genome a set of books, encyclopedias, you could just take each page of it, sequence it, and do a page by page sequencing approach, or just take it, shred it apart into a billion pieces, and be able to put it together computationally in all-in-one sequencing strategy. Both these strategies were adopted for doing the first reference human genome sequence, and that led to this famous set of meetings. Most of you recognize the people here, and the idea here it was the human genome project announcement, where they declared the reference human genome. Okay? But then around that point there was a change, a shift in technology. Okay? From Sanger sequencing, which was the state of the art, we moved into something called the next generation sequencing. In a minute I'll explain what this next generation sequencing is, and again also a technique that was primarily standardized and invented in the UK, but moved on ahead to US and became very popular as the next generation sequencing. And instantly an Indian was involved in here in creating at Oxford. Okay, many of you would recognize the name. And the way this technology worked, or rather Shankar Balasubramanian, when he figured it out, was a chemist at the Oxford, where he sort of figured out the crux of doing this method. It's called reversible terminator chemistry. You could take a piece of DNA, add adapters to it, put it on a glass slide that would have corresponding adapters, and be able to generate clonal populations of that fragment, which could be imaged now using a laser. When you shine, you can get different colors, at the bottom pertaining to each nucleotide, and you could do this multiple times, and over time you could generate a set of sequences. Now this was massively parallel, okay, and in a single flow cell you could do a human genome. It took about a decade for this to become a standard off-the-shelf product, but nevertheless now it is available, and that led to the sequence explosion, where going on from doing that red line that goes down the middle is actually the cost of dwindling cost of sequencing the genome, and that's the number of years on the x-axis and the price in the y-axis. Okay. Around 2007, when it became affordable to do single human genomes or personal human genomes, is when people like me were starting our own labs in India. And around the same time, we had a number of dignitaries around the world. Several of them you could recognize, James Watson, Fred Venter, and others, who also had the personal genome sequenced. So there were about 6 human genome sequenced in 2008, and they were largely from 2 parts of the world. Okay, one either from the European or the African part, which we had representative sequences, or from the East Asian, the Chinese and the South Korean and the Japanese genomes. Okay, these are all individual genomes, but largely the bulk of the population of the humankind lives in the Middle East and Central Southeast Asia, which was underrepresented. That's where my colleague and my colleague Dr. Vinod Skaria and myself stepped in to put in the first Indian personal genome, and this also was a template for us to go back and build upon what is today. We have built a larger program around it, is to understand what does it take to implement something from scratch, because this is not a technology that was really in textbooks. We have to learn it every bit of the way, but nevertheless that laid the foundations for personalized and precision medicine in India. And currently what we realized that one genome was sort of not the typical representative genome. India is a very diverse country, so you need to do a lot of genomes around here, not only in India but around Southeast Asia. So we ended up doing the first genomes for Sri Lanka, Malaysia, Philippines, and so forth. Now we work with a large number of collaborators to set up the Southeast Asian genomes and exomes. I'll talk about it. We also work with a large number of collaborators in the Middle East to set up something called the Almina, which is a large variation database which has about 26 million variants now. Okay, about 2,000 whole genomes in it, and something that can be extensively used by clinicians. Same with SAGE, something that can be used extensively. I'll talk about it. So it all boils down to how different are we from each other. Apparently we are very close to each other, and we differ only by a very few percentages. That's less than 1%, and it's all about the single nucleotide variations, the insertion deletions, and the structural variations that each of us inherit. Okay? That's what we are trying to measure, and that led to a new specialty called genomic medicine that involves using genomic information about an individual as part of his or her comprehensive healthcare supervision. And this is the whole field that sort of all of us are here gathered to see how can we collaborate with each other or work with each other to actually implement in the clinics. So one of the areas where we had immediate application, there are only very few areas till today where genomics can really be applied in clinics. Okay? Among them, rare genetic disorders is an area where it can be readily applied, and it is already being done in many parts of the world. Okay? Most of you are clinicians, you know that what is rare genetic disorders. There are about 7,000 of them that have been documented in literature. About close to 1,500 occur very frequently, and that becomes of keen interest to clinicians. In the context of India, it's even more important because there are 70 million people, okay, who suffer from a genetic disorder, and several of them are rare in nature. Collectively, cumulatively put together, this is a large number to be addressed. Okay? And you can see, look at the statistics. Okay? That's something that we wanted to sort of change. So when the government sort of worked with us, we worked with the government of India in trying to develop proof of concept approaches. That's what we do as a research institute. Okay? We don't really walk into a clinic and say we have something to offer. No, we develop proof of concepts with working with government agencies and with key hospitals, the tertiary hospitals, to see how this could be implemented in the settings of India, and then scale it up to rest of the country. So that's where this program comes in, Genomics for Understanding Rare Disease India Alliance Network. Okay, we turn what is the lacunae in the Indian settings. Okay, there's a large population. Yes, that's a lacunae, but it also represents a diverse genetic pool. Okay, where there is stratified population, high level of endogamy. That's fantastic if you want to figure out inherited diseases. Okay, lack of baseline data and demography, but that could be turned around. Okay, in case of rare genetic disorder, there is always going to be a little bit of a issue because we are not able to cover all the rare genetic disease, but you could really go back after familial cases, and then that does not become a major issue. So we set up this program between Dr. Vinod Skade and myself at IGIB, where a lot of clinicians, believe me, this is a research program, okay, not a clinical service, okay, where clinicians send samples of patients with inherited disorders, okay, and these are a wide variety of disorders, right from primary immunodeficiencies to mitochondria to cardiac to neuronal origin. We take about a dozen of them, and there's a very strict inclusion criteria, of course. We do genome sequencing, exome sequencing, or sometimes even just panel sequencing as the case be, and we'll be able to find a genetic mutation that causes the disease. But about 50% of the cases, give or take about 10%, we don't find the genetic mutation. In that case, we will do additional workup, either do a biochemical assay, build zebrafish models, or do other additional computational workup. Currently, we have about 150 collaborators representing about 40 major clinical centers around the country, and impacting about 3,000 patients, 3,000 families that work with us. Okay. So largely we have three major approaches. Okay, we either do candidate panel target sequencing, which is not our favored approach because this is biased towards known mutations, and most of the mutations have been captured in the Western world, okay, and may or may not have relevance to the Indian settings. So you will not be able to discover something new using candidate genes or panel target. That's one of the limitations. So we don't use it very often, but we do use it when there is a very telltale sign or clinical symptom that points to a mutation. We do use that. Largely the bulk of the work is going into a whole exome sequencing because it's a very small component of the genome, and very well structured programs and protocols exist that we can implement it. Whole genome sequencing we only use when it's an exome negative case, okay, but there are limitations in whole genome sequencing as listed out there, but nevertheless we are able to implement it at some scale. So exome is nothing but about 1% of the genome that codes for the protein, and since it represents about a large subset of the inherited disease, that's about 85% of inherited diseases account to about mutations in exomes, we are able to use this effectively, and be able to sequence exomes or genomes, run a set of computational pipelines, and be able to identify a causal variant. It's not as simple as it sounds, but I'm just summarizing it here. So one of the engines that drives all our computational is something called the SAGE, Southeast Asian Genomes and Exomes, which not only control in the absence of 100,000 genomes like the UK or the US programs or very country-specific programs that are out there in the Western world. Okay, we do not have one. So what we do is we have super controls. That is about, we use centenarian genomes. Okay, if you are going to look at inherited diseases, okay, we use centenarian genomes as a filter. If the mutation exists in the centenarian, we assume that that's probably a bystander effect or a variation that did not contribute to it because they have lived 3 times their lifetime. They were born in 1920s and they have lived 3 times their lifetime. So a normal individual of that in 1920s have lived almost till 29.5 years only. We also have a lot of normal healthy family cohorts, and we also aggregate a lot of population scale data from our collaborators. Okay. Currently SAGE has about 1,200 genomes and exomes, about 169 million genetic variants, and all this is published, freely available. People can go put their favorite variant information. It will come back and tell you what is the allele frequency of it in major databases including SAGE. So I would encourage you to use it. So here is an example of how Guardian runs. Okay? I am not going to go into all the different cohorts, but there is a cardiac meeting. So I have taken an example out of a collaboration that we had at AIMS New Delhi, All India Institute of Medical Science New Delhi, especially spearheaded by one of my favorite collaborators who is unfortunately no more with us, Dr. Rajneesh Juneja. He had a cardiac episode earlier this year, and unfortunately is no longer with us. But his colleagues are really Ambuj Roy, Nitish Nayak and Gautam are really taking it forward. Okay, so we enroll anywhere between 50 to 100 individuals per cohort. In this case, it was rare cardiac channelopathies that we wanted to look at. We did whole exome sequencing on 52 index spaces. Okay, 41 have gone through the pipeline. As you can see, the outcomes, about 41% were able to find a variant that could go back and sort of explain the disease that's there in the patient, and that becomes clinically relevant. Again, about 10% we need further clinical data. We cannot otherwise solve the case. There are more than one mutation prior type. But about another 48%, clearly there is no candidate. That's the prime sets for whole genome sequencing. I'll give you one example. Here's a family with a rare familial long QT syndrome. Okay, this was primarily referred by Dr. Juneja and then followed up by other clinicians in his hospital. Okay, as you can see, a large family with long QT deafness, weak eyesight, and various presentation. So two things were not really clear. What is the mode? Was it autosomal recessive, and the provisional diagnosis was congenital long QT syndrome. After doing all the exome sequencing and running the pipelines, we actually came up with two variants. Look like it's a compound heterozygosity or a double heterozygosity. Okay, both of them in KCNQ1. Okay, and could clearly explain that it's either Jarvell-Lensen syndrome or long QT syndrome, JLN or long QT syndrome, either one of them. Okay. Now, summarizing this whole work, looks like one of the mutations in KCNQ1 is inherited from the mother's side and one of them from the paternal side, father's side, and the children actually get both the mutations, and the affected individuals have two mutations in them that cause it. KCNQ1, like most of you know, doesn't require an introduction to this audience. It's a potassium channel, and mutations have been studied widely and known to cause long QT. So we think one of these mutations has been well documented for long QT, but the other one is not found in the 1000 genome exact for the internal control. So it's a possible novel mutation. In this case, you go back and do functional validations. Okay, that's the usual course that you do. This is the case of cardiac hypertrophy that came out of Dr. Sandeep Seth's clinic, and again at AIMS and Dr. Rao at Delhi University. Okay, in this case, multiple deaths in the family. Sequencing revealed a mutation in a novel gene, okay, which has previously not been implicated in cardiac hypertrophy. So what do? The favorite approach that we take is go back and build zebrafish models. Unfortunately, the video is not going to play here. It has been my computer. We have seen that's the heart of the zebrafish. Okay, and if the video played, you have seen a nice two-chamber heart beating, and in this case, the chambers actually are enlarged, thickened, and they also have they'll miss a few beats once in a while. Okay, so unfortunately, the video is not playing now. So you get opportunities to do disease modeling, and we validate them. You could also look at the effect of the mutation. Okay, this is something that is going to hit the clinic a few years from now. It's not readily there. Okay. For example, we have taken the case of TBX5 mutation, which is known to cause Hartung-Hand syndrome. Very famously studied the G80R mutation that's shown in red, but then there are variations around it. Okay, this is the human and the zebrafish sequences. You can see almost identical. You cannot differentiate them. Okay, so the effect of these three variations on this particular mutation is what I'm going to show you. Okay, so that's a zebrafish two-chambered heart. Okay. And when you suppress TBX5, you get a linear heart. So in zebrafish, it's a two-chambered heart which is folded upon itself. Now, in the absence of TBX5, it remains a tubular heart. It remains a single pipeline. Okay, so that's what happens in zebrafish. Unlike human, you don't see a lot of structural variations, but you see the complete twisting upon itself missing. Now, you can put back the human RNA, and you get back the two-chambered heart again. Now you can put the human mutation, you still get back the tubular formation. Now you can put the variation 1, 2, and 3, and the effect of the tubulogenesis, the changes, the severity of the disease changes. So you can actually measure how simple variants around a mutation actually affect the presentation in a model organism. I'm sure it happens in humans also. So to summarize all this, we have a program called the Guardian, which is a discovery platform which we use to discover the novel mutations. Then we also have a second platform called the GoMed, Genomics for Enabling Medical Decisions, which is a clinical platform. It's a clinical service. Okay. Whatever we discover here goes into this platform. We have about 160 high-end tests. Close to about 5,000 plus patients get benefited every year. This is done free of cost as a proof of concept. We don't intend to compete with companies. We want to work with them. So we also transfer these tests to commercial companies once we are sure that the assay is working fine, and we also keep it free of cost because there are a lot of people in India who cannot afford it still. So those who cannot afford it, clinicians can send to us. It might take about 8 weeks for us to get back with the results, but we do get back. Whereas the companies do get back with a much faster turnaround time. So what do? We enable clinicians to make precise diagnosis. We enable families of healthy children. We identify novel genetic variants, which is the template for new biology. So in a nutshell, we focus on the individual, not an average response to therapy, and that's personalized medicine. Okay. We also do a lot of training, booklets, course materials that Dr. Vinod and myself write. We also work with the likes of Frontier, and we had one a couple of years ago. We had a CME here. We also do a lot of exome sequencing workshops, whole genome workshops, hands-on. So feel free to reach out to us. And we do about 8 CMEs and about 3 workshops every year. And with that, I'll thank a set of very bright set of graduate students, PhD students in my lab and Vinod's lab who have contributed extensively to this work. Of course, Mohammed Farooq, who is also a clinician. Vinod and Mohammed Farooq are actually my clinical collaborators at IJB. Of course, a fantastic set of clinicians around India, patients and families, and all funding from Council for Scientific and Industrial Research India. Thank you.